be at Northwestern. You know, John Franks is still there. All the some original people from 1971 are still there. But COVID's shut it down. So when that happens again, maybe next fall, maybe, that's a great opportunity to visit Chicago because you go to the conference, it's in Northwestern, you take the train back to the city, la di da di. It's possible.
Great.
Yeah. Especially, is this a hyperbolic meeting? No. You got, is Federalis a hyperbolic school? I mean,
I think so.
I mean, is it? It's partially hyperbolic over at EPA. I classify everything. There's Ohio is where they do, you know, not hyperbolic coding, like Brian O'Crawl does at Northwestern. Buki does partially hyperbolic. Chicago with Amy is partially hyperbolic. But also Zimmer program is there. Whatever. Yeah.
Cool.
It'd be great if everybody at this conference could show up in Chicago, and then you know you skip all the talks and just go hit the city. Just tell them to record all the talks on Zoom, then go spend a week in the city. That'd be good.
Yeah, when I was a student, I remember there was a conference for the anniversary of Jacob Palace at Búzios, which is a beach town near to Rio, full of beaches. You can just go. There are, I don't know, a finite number of beaches, but this finite number is big. And it was for 2 weeks, and it rained all the time. I remember the last week, there was one day that the last day it was sun. And then I was a PhD student, very, very geek, and my colleagues were saying, let's go to the beach. And I was thinking, no, we shouldn't go. And then we end up skipping one talk and going. And then when we were there, I was feeling guilt, but I look around, the whole conference was there.
Well, yeah, you did your 2 weeks. Come on.
My God. But I felt even more guilt because I thought, who is in the talk? If everyone is here, who is there in the talk?
Actually, speaker's talking on a cell phone to the.
Yeah, right now we could do this. These were some years back, so maybe we didn't have this technology, but now we could just do this. Okay, let's do from the beach.
Yeah, I can't. None of us. We're all waiting for this COVID thing to go away.
Yeah.
Back to normal.
Yeah, Luciana, it's you are the boss.
Davi?
Let me share my screen.
All right.
I don't know if you want to wait like 2 minutes to start. So up to you, Luciana.
Maybe yes. Okay. 2 minutes.
In the meantime, again, if people feel comfortable having their cameras on, I would really appreciate this. It's very weird to talk by yourself in front of a computer with no faces.
Yes.
It's lonely.
It's going to turn us even more crazier after this, because we are already a bit, but I think it's gonna affect our psychological after all these things. I cannot record classes. I was talking earlier with Isaia. He was saying that he records some classes. I cannot record class. I need someone, at least one student, with the camera talking to me, because it's impossible. So my camera will be on, Davi, at least this.
Having the cameras on actually is good for 2 things. You actually feel like people are listening to you. And the second one is if you say something very stupid, you can look at people's faces and realize you said something very stupid.
You can figure it out. No, yes, I think that to be lonely speaking it for a screen, it's not good. Seems like you're crazy.
Yeah. It cannot bring anything good for your self-esteem and I don't know.
Okay, let's go. And it's my pleasure to introduce Davi Obata with his main course, Stable Ergodicity, second day. Please, Davi.
Thank you. So I just realized that the strips in my shirt make some weird
Sorry, David. I forgot again to record. I apologize.
Okay.
Yeah. Okay, you can start. Sorry.
Yeah, so hopefully my shirt won't make you dizzy. I just realized this, that it caused some weird effect with the camera. So yeah, so let's continue with our second day, talking about stable ergodicity. So in the first day, I talked a little bit about this Pugh-Schub's program, their conjecture about proving that among partially hyperbolic systems, stable ergodicity is the typical thing among volume-preserving partially hyperbolic systems. And one idea to go about proving ergodicity of a system is to, for a partially hyperbolic system, is to, I don't want this, I want this, is to check accessibility. So accessibility meant that for any 2 points in your manifold, you could connect these 2 points by a path contained, which is a concatenation of stable and unstable manifolds, and with another condition called center bunching, which I didn't define and I'm not going to define it now, you could conclude ergodicity. So this is one possible approach to prove ergodicity among partially hyperbolic systems. But one difficulty here is that if I give you one example, it can be really, really hard to prove that it's accessible. So accessibility means you want to go from any 2 points in your manifold just by moving inside stable and unstable manifolds. So this can be a very hard problem if I give you one example. So the types of results you see is that densely you can obtain accessibility. So you will have to perturb. But for a given example, this can be hard. Well, so this is one possible approach of proving ergodicity. Another approach is to use Pesin theory, which I'm going to describe in a little bit. I'm going to give more details later on today. But if you deal with Pesin theory, the idea is that you want to find transverse intersections between stable and unstable manifolds in a non-uniform hyperbolic setting. So you have two difficulties for a given example. The first one is that you want to verify non-uniform hyperbolicity. So you want to verify existence of non-zero Lyapunov exponents at almost every point. A second thing that is difficult is that you want to, once you have this information, you want to find transverse intersections between these manifolds. And if you ever worked with Pesin's stable and unstable manifolds, you might know that this is actually a very hard problem. So you have those two difficulties, but it's also another possibility of strategy. So the idea of today is to explore the second type of strategy. So let's see how we can look at Pesin theory and be able to find ergodicity for a certain class of example, for a certain type of example. So let me just define at a first moment what Lyapunov exponents are. Then I'm going to introduce the example. Then I'm going to talk a little bit more about Pesin theory. So a number, we can say that a number is a Lyapunov exponent at some point P if there exists some vector, a non-zero vector, such that this number captures the exponential growth rate of the derivative along on this point, along this acting on this vector. So if you have this, you can say that this number is a Lyapunov exponent for this point. And given some invariant measure here, for example, for a C1 diffeomorphism, you have this Ozelledet's theorem, which I'm not going to state precisely, but a consequence of this Ozelledet's theorem is that for almost every point here, with respect to this measure, this limit exists for any vector. So actually, one of the things you obtain is that you have at most the dimension of your manifold of different possibilities of Lyapunov exponents. And we say that a measure is hyperbolic if for almost every point, all the Lyapunov exponents are non-zero. In the volume setting, I'm gonna change the name to non-uniform hyperbolic. So I'm just gonna say that F is non-uniform hyperbolic if the volume is a non-uniform hyperbolic measure. Okay. So I want to introduce this Bézier-Carrasco example, but before, let me just say a couple things about these Vienna examples. So if you were here if you're here for Stefano's talk, he explained this philosophy, which is really good, that you have a system, you try to understand the Lyapunov exponents of the system. So this can be a hard problem. This usually is a hard problem. Something you can do to make your analysis simpler is to add some random noise. So he talks about doing some random perturbations where you add some translations depending on some interval, and you add some random noise. And because of this random noise, this can help you to do this analysis. So here, this type of philosophy, it's also appears in examples in dynamics, where you're coupling your system, instead of a random noise, you couple it with some hyperbolic system on the base. This is the idea of what happens in these Vienna maps, which was introduced by Marcello in 1997. And in his paper, he introduced two types of examples. The first one is an endomorphism in dimension 2, where the idea is that you couple quadratic maps with some expanding map on the circle. A second type of example in his paper, it's a diffeomorphism in dimension 5, where you couple NO maps. So I'm not defining these things, but if you know the names, it's okay, but I'm not going to use them. But it's just to give an idea where the example came from. So you couple these NO maps with a solenoid attractor, which is hyperbolic on the base. And he proves in his paper robust non-uniform hyperbolicity of these systems for this type of construction. And the idea of one of the ideas of Bézier-Carrasco example is to look at the second example where you have a diffeom, but you have an NO map and a solenoid attractor, so this system is not volume preserving. So the idea is to construct a similar example, but which is volume preserving. And the way you translate this is you look at NO maps and you change NO maps by standard map, which I'm going to define in the next slide. And you change solenoid attractor to a volume preserving Anosov diffeom. So the idea is to couple a standard map with an Anosov diffeom in a way that at the end you get something non-uniform hyperbolic. So I'm going to make this construction now, but this is some previous example that have similar flavor to this Bézier-Carrasco example. Okay. So let me talk about the standard map. So if you look at T2 as R2 quotient by 2 pi Z2, and you add coordinates Z, Ax, and Y. So for each n positive, you may consider the Shirikov-Taylor standard map. So forget about the picture at the moment, which is given by this formula. So you take x, y, you send this to n sine x plus 2x minus y in the first coordinate. In the second coordinate, you put x. So a first thing you can do is you look at this formula and you look at the derivative of this formula. So if you look at the derivative of this formula, you get the following matrix: n cosine x plus 2 minus 1, 1, 0. And what happened is, you see there is a n cosine x here. multiplying. And if n is very large, and if cosine is not close to 0, then this entry here of your matrix becomes large. So this is translated to, you start to see some expansion for like almost horizontal vectors. So if you have some vector close being horizontal, you start to see some good expansion. The problem here, and one thing is that this matrix has Jacobian 1. So if you see expansion somewhere, you should see contraction at that as well, because the determinant has to be 1. And one thing that can happen here is that whenever cosine x starts to come close to 0, then you could start to get something like 0 here, and you start to get rotations. So you have matrix close to being like 0, -1, 1, 0, where horizontal vectors start to become vertical vectors, and this adds some difficulties in this model. So one way you can think of this is if you look at your torus, you have a huge area of your torus where you see good hyperbolicity. Good hyperbolicity means, in this case, means you see good expansion in horizontal vectors. And if you see good expansion for the path in horizontal, in vertical vectors, if you want. But just looking at the expansion, there are two problematic regions, which are the regions where cosine becomes close to 0. And those we call critical regions. So if you want to precise some rate of expansion, then you can give some precision of how large these critical regions are. But the idea is that you have two vertical strips where are the critical regions. Those are places where your vectors can be rotated, and everywhere else you'll see some good hyperbolic behavior. Two properties, like I mentioned, is that it preserves Lebesgue measure. And because of those rotations, I'm gonna say this, but I'm gonna actually just define this dominated decomposition thing tomorrow. But it does not admit a dominated decomposition, meaning you cannot have a good splitting of your tangent bundle in the entire manifold for this in good dynamical directions for this standard map. In a famous conjecture by Sinai is that you see that as n increase, the size of these hyperbolic regions, they decrease, which means that the size of your the size of the critical regions, they decrease, which means that the size of the hyperbolic regions, they increase. And it's a famous conjecture that if n is large, then there exists a positive Lyapunov exponents in a set of positive volume for the standard map. This can be translated using Pezin's entropy formula to, if n is large, your system has positive metric entropy. Okay, so this we don't understand this. We don't have answers for this conjecture yet. So the standard map is a hard diffeomorphism to deal with. And one way to make analysis simpler is to try to couple this with a hyperbolic base, which you can make this analogy with Stefano's talk as adding some randomness in your system.
Can I ask on this? I mean, this sine term is a shear, right?
Mm-hmm.
Or is it the 2x? When you looked at your matrix, it had determinant 1.
Yeah.
So that means that you're dealing with a shear.
Yeah. But I guess that the main thing here is that you want to understand if this hyperbolic part is dominant.
So
Okay.
why would it have positive Lyapunov exponent? Just because of that term?
Just because of this term. And if you look in your phase space, in your T2, what's happening is that you see good expansion in most of your manifold. So I guess one good maybe, again, if at some moment you're bored in this talk, something you can try to draw is like if you connect a horizontal line like this and see what the image is, and you start to see some types of the pictures that appears with standard map that gives this idea of good hyperbolicity.
Yeah, thanks.
So this is kind of slow today. Okay, here. So the idea is to couple this with some hyperbolic thing. And so we fix some hyperbolic matrix in SLO2Z. In the two torus, we define this projection in the first coordinate, takes x, y, sends this to x0. And now we want to couple these things. So we look at T4. We look at coordinates x, y, w, z. And this is the Bejer-Carrasco example. For n here, a natural number, you may look at the skew product. So what is this? First, you look at wz, and you see that you're just acting by your Anosov to some power depending on n in wz. So in the second torus, you're just acting by your Anosov system. In the first torus, you're adding your standard map and xy. And again, the critical regions, they were those strips that depended on x. And the idea is that those are the bad sets. And the idea is that you add translation in the x direction of something that depends of what's happening in the hyperbolic part of this Q product. So you add a translation in your x direction of something that depends on the other two coordinates. Okay, so this is the Bejer-Carrasco example. And the 2n here is just so that the hyperbolicity you see here dominates whatever appears on this part, and you get at the end something partially hyperbolic. Some properties of this thing is that, well, if n is large enough, you have a partially hyperbolic system. So you have a decomposition of the tangent bundle into three parts, a stable part, and here there are two stable parts. This should be U. So you have a stable part, unstable part that comes from the Anosov part on the basis. So these are one-dimensional. And then you have a center direction, which are the fibers. They are actually given by, in the coordinates I wrote, they're given by R2 times 0. So they are the fibers. So this is one property. Yeah, so sorry, you have to forget this S here. Another property is that you cannot really decompose the EC direction into any further because you have some standard map acting there. Again, I'm not being very precise about this, but it's just to say that you have a genuine two-dimensional center system. It's not something that you can decompose into two one-dimensional bundles in the center. And what Bejer-Carrasco proved in Pierre Bejer and Pablo Carrasco in 2014 is that there exists some constant between 0 and 1, such that if n, your parameter, is large enough, then this system, oh, I didn't say here, but the example preserves Lebesgue measure. In the second torus, you're just acting by your a to the power 2n, which has determinant 1. In the first torus, you have the standard map part that also has determinant 1, so it preserves value. Okay. All right, and then, yeah, sorry. So what they prove is that you have some constant and your system is non-uniformly hyperbolic, which means that you have non-zero exponents for almost every point. And they also give you that the absolute value of the Lyapunov exponents in the center are larger than constant log n. And they prove that this is C2 robust. Their proof does not use ergodicity of the system. They don't have to know ergodicity of the system to prove that. And since the action on the center, on the fibers, are being given by these standard maps, plus some translation, but the determinant is 1 on the fibers, the existence of non-zero Lyapunov exponents in the center actually implies the existence of 1 positive and 1 negative exponents, because the sum of the exponents will have to be 0, because the determinant is 1. Okay, so they have this example, which I find really nice. And the goal for today is to prove that this example is C2 stably ergodic. So you want to prove ergodicity of the example and of any system volume preserving system sufficiently C2 close to it. Okay. We don't know about accessibility of this example. And this is one thing, because accessibility can be very hard to prove. Okay. All right, so let me give you a few things. So from Bejer-Carrasco's theorem, we know that if Fn, well, I'm going to call F just to forget about this index here. For n large, what Bejer-Carrasco tells you is that you have a non-uniform hyperbolicity. In particular, if you combine this information with Ozela-Det's theorem, this tells you that for Lebesgue almost every point, there exists a decomposition of your tangent space at the point P, which is given by the following four directions. So you have the hyperbolic directions, the uniform hyperbolic directions that comes from the partially hyperbolic splitting. In the center bundle, or the center direction, sorry, at this point is decomposed into two one-dimensional directions, which are the Ozela-Det's directions. And you have numbers. So you have two negative numbers, two positive numbers, such that if you look at the asymptotic growth of your thing in each of these directions, what you're going to see is these numbers. So this is compiled in this equation here. So if you look at this limit, in each of these bundles, you get the number, the Lyapunov exponent. Okay, so this is what you get from Bejer-Carrasco example together with Ozela-Det's theorem. So I want to describe a little bit Pezin, a little bit more Pezin theory, Pezin's manifolds, and things like this. So let me define first what a Pezin manifold is at the point P. So this is the set of points in your manifold that the distance between the orbit of P and Q, if you look at Fn of P and Fn of Q, they converge to 0 in an exponential rate. So this is captured by this thing. And you can define similarly Pezin unstable manifolds if you look at the past. So a point here would be in the unstable manifold if you look at the distance between Fn of F minus n of P and F minus n of Q, and they are converging to 0 in an exponential rate. Okay. And a key thing here is this Pezin stable manifold theorem, which states the following. In our setting, so I'm stating the theorem in our setting where we know that F is non-uniformly hyperbolic. You have the composition for almost every point of the tangent space. And we can say that for almost every point, that set that I defined before, the stable manifold, Pezin stable manifold, and the unstable manifold are actually C1 immersed and locally embedded submanifolds. And at the point P, their tangent space is tangent to the Ozela-Det's directions of the negative part and tangent to the Ozela-Det's directions of the positive parts if you're looking at stable or unstable manifolds. The other thing that the theorem tells you is that you may wonder about the size of these manifolds. And the size of these manifolds, well, for every point, you have some size given by this RP. So the manifold contains a disk of size of radius RP, but this size varies measurably. So the size of your manifolds, the size of these disks contained in your stable or unstable manifolds are, they change measurably with your point. You can get some continuity if you look at some type of losing blocks for Pezin's, for this type of theory, which are called Pezin blocks, but the thing is that these things change measurably. Some important things when you deal then with Pezin's manifolds is the following. So one thing is that Pezin manifold requires higher regularity So you were working in a C2 frame or C1 plus holder frame setting. You can do Bayesian theory if you have C1 plus an hypothesis of dominated splitting. This is also possible, but in general, Bayesian theory is something of higher regularity. Another thing is that, so you have your manifolds, they are tangent to these directions, ES and E minus and E plus and EU. Well, the hyperbolic directions, they're okay because they come from a splitting defined in your entire manifold, some continuous splitting, so they have good angles between them. But if you look at those LHDET's directions, it can happen that those two directions, they can come arbitrarily close together. This comes from the fact that those LHDET's directions, they also change measurably with your point. So in particular, the angles between those two directions could be arbitrarily small at some points. Okay, so you have the angles between those two directions being could be arbitrarily small, and the other thing is that the size of these manifolds that comes from this function R here can also be small. Okay, so those are two things to keep in mind. So in particular, what happens is that yeah, so this is what I say here. The size of the manifolds can be small. If they are small in the center direction that comes from this part, because the uniform directions, you have this stable manifold theorem that you can apply that tells you that they have good uniform size. So if there is problem of your manifolds becoming small, that comes from the center direction. So Pezin in that same paper from 1977, which I'm not sure if I mentioned that before, but he proves the following. If volume is non-uniformly hyperbolic, and if you have C2 regularity, then volume can have at most countably many ergodic components. So this is already, the proof of this uses this generalization of Hopf type of argument to the non-uniformly hyperbolic setting. Actually, what he proves is the following. Every ergodic component, so mu I, has a specific form, and the form is mu I of some set, measurable set C, will actually be the restriction of volume to some set xi. So that means that there exists some set xi of positive measure, such that your measure mu I is given by the restriction of volume to this set. Okay, so let me try to describe now what the type of strategy will be. We want to prove that, so we're just going to focus on the proof of the example itself being ergodic. So if the example is not ergodic for some large n, then you should have at least two different ergodic components, right? So if something is not ergodic, then it should have at least two different ergodic components of volume. And a possible approach to prove then is the following. There are two steps in the approach. The first one is to prove that you have two sets, lambda 1 and lambda 2, each of which has positive measure for mu I. So lambda 1 has positive measure for mu 1, lambda 2 has positive measure for mu 2, such that for any point in the first set, lambda 1, let's say, the Bayesian stable manifolds intersect transversally the unstable manifolds of a point in lambda 2. If you have this thing, then Bayesian theory, so Bayesian's proof in his paper, you would actually get this, that mu1 will have to be equal mu2. And the thing of going to the second part is actually just doing the same type of strategy of Hopf argument that I explained last time, using some Bayesian blocks where you have some uniformity of certain things. But the hardest part here for this example would be to obtain the first one. So an idea would be you have set lambda 1, you have set lambda 2, and you want to prove that points here, the stable manifolds, Bayesian stable manifolds of points here are intersecting transversely unstable manifolds here. So you should have something like this. Okay, so this is the main idea of the proof, is to obtain transverse intersections between those things. A difficulty is you have submanifolds, you want to find transverse intersections between them. You want to control, to find these things, you want to control the size of the submanifolds and kind of the direction where they're going. So that's what I'm calling here geometry. So you want to control size and geometry of these manifolds. Size meaning you have to have decent size. Geometry meaning you want to know that they go in certain directions. Because otherwise you could have a picture like this. You could have 2 points close together. Their manifolds, the stable manifold could be large. The unstable manifold could also be large, but if they don't have good angle, you wouldn't get an intersection. Or they could even have good angle, but the manifolds are just not long enough to get intersections. So you want to avoid those two things. So to do that, you want to say that they are in good directions. At the same time, they have good length. To say that now you get transverse intersections. So this is the main difficulty. And because you're only dealing with Bézier theory, you don't have at first good control of size, and you don't have at first good control on these angles. So those two things, they play a role here. Okay. So our remark is that just with Bézier theory, you cannot get, you won't get ergodicity.
But can I ask, if you have control of something like, what do they call them, cone structures?
Mm-hmm.
Does that guarantee the good angle and the good length?
So that would guarantee good angle. So for example, if you're in a setting where you have what is called dominated splitting of the Ozelades directions, this solves part of the difficulty. This will solve the part of the angle. And then you have to work with the size part. You will have to work with obtaining size. Here we don't have, so this is why in this setting, you would add both difficulties at the same time, because you don't have these cones. So you don't have the good angles at first, and you also don't have the size. So you have to work to get those two things.
Thanks.
Okay. So our remark here is that you don't have these things. So the proof has two parts. There is a local strategy and a global strategy. And a few words about each of these parts before we jump into more details is that the local strategy, the idea is that you want to use a quantified version of Bézier theory. So we want to use some quantified version of Bézier theory to obtain lower bound on the size of the manifolds. And it turns out that in the points you're looking at these things, you can also get some control of the geometry of these manifolds of these directions. Once you have this local strategy, you use more the specifics of the example for global strategy to actually get intersections between these manifolds for different points. Okay. So let's jump first into the local strategy. So there is one key main ingredient, which is a version, which you can think of this as some quantified Bézier type of theory for surface defills that appears in a paper of Sylvain Crevizier and Henrique Pujals. So actually, let me state the whole thing, and then I'm gonna walk through what these things are. So suppose you have a surface defill, and you have a you have a surface and you have a situ defill of this surface. And suppose you have four constants between 0 and 1, such that they verify some numerical condition. Then what happens is that for any point in that surface having a direction with the following property, for any positive time, if you look at the action of the derivative on that point in that direction, you have contraction, good contraction, but you also have a good control on your on this action from below, given by this sigma tilde. So this is a contraction type of hypothesis. of condition. A second condition, so before I state this, if you go back to like, I don't know, if you ever seen the proof of the stable manifolds theorem in the hyperbolic setting, for example, or more general, there are two types of hypotheses. One is that your stable direction is actually contracting. The other one is this cone condition that Stephen was mentioning about, which is translated by dominated splitting. So this is telling you that if I want to look at something at x, I go to f of x, I look at this cone, and I apply my inverse dynamics, these cones are being contracted. And these types of things, they are very good because you want to apply what is called a graph type of argument to find your stable manifold. So you have a contraction hypothesis and you have a domination type of hypothesis, which is translated to having contraction of cones. Here you also have those two things. You have a contraction type of hypothesis, and this expression here captures the domination part of the hypothesis. So I'm just gonna, if you think of like hyperbolic case, this would be like lambda s squared, and then on the bottom you should have something like lambda s lambda u. So you would cut this thing here, and you would get lambda s divided by lambda u being smaller or equal than something. So this is the type of domination hypothesis appears. But again, being controlled by those constants that appear before. So if you have this, the theorem states that there is a stable manifold at this point tangent to this direction, and the size only depends on the constants and the C2 norm of your diffel. Okay, so it allows you to construct stable manifolds tangent to some direction at some point for the diffel with uniform size depending on some quantities. And there is some numerical condition to verify. Okay, so let me go to this numerical condition and let's try to see what this would represent in our setting. So the idea is that, the theorem is for surface diffels, but now we want to construct stable manifolds. But we know that, so we're in T4, we know that in the hyperbolic part, we have good size of these things. So we only care about measuring the size at this moment of what happens in the center direction. And if you give me a point and I look at the dynamics along the center manifolds, the center manifolds are just the fibers of this system. They're just the two torus. So this will induce a sequence of diffels of the torus. And I can look at this sequence and try to construct stable manifolds for this sequence. And if you do this for some special point P, which I haven't precised yet, and if you do this and you try to understand now what is what with respect to the previous theorem, well, we want to get something like this that verifies something like this. So the translation would be, for a stable manifold, for example, would be sigma tilde, the lower bound. It's a lower bound for the derivative on the center, for the conorm of the derivative on the center. So you just put the worst it could happen. So this gives you 1 over 2n, for example. This upper bound, I will translate this to the exponential of the negative Lyapunov exponent, which, so Bejer-Carrasco, they tell you that that's the absolute value of the Lyapunov exponents are bounded from below by constant log n. So if I look at this, this will give me exponential of minus c log n. And once you have this first inequality, you have the second one for free, because the determinant now on the center is 1 because of the standard math. So the bottom part is 1, and the top part is you just squared everything you got from the first part. So here you get just the square of the previous part. Okay, and now you plug this into the inequality that you want to verify. This inequality appears in the proof, so it's something that you need. So if you plug in this thing in the inequality, you get that 1 over 8 n to the power 3c minus 3, it's greater than n to the power minus c. Roughly, this would give you that you want c to be at least 3 over 4, roughly. So in the Bejer-Haesco example, in their statement, you have some c. It's not that precise what c is at the moment, but to apply this type of technique, we need a better c. So this is a proposition. What you do is you apply, you can precise more the construction of the proof of Bejer-Haesco to prove that for any delta, if n is sufficiently large, you can actually prove that the exponents have absolute value larger than 1 minus delta log n. So you can be very close to log n. And this is good if we look at the type of estimate we want to apply this thing to. Okay. And now you want to look at which points you apply these things to. So you define this set z minus, which are, so you cannot really apply the thing, if you really want to apply that thing, you cannot really apply for the Lyapunov exponent itself, like exponential of the Lyapunov exponent itself. You need to add some error, like some epsilon. So that way you have tools such as Please lemma, which unfortunately I won't have time to go into details here of that part, that allows you to obtain many points for your measure where you verify the hypothesis of the type of construction. So this is, you codify this into these 3 sets here. So z minus is the points where it's good to apply the construction for stable manifolds. You have good contraction. Z plus is the points where it's good to apply the construction for unstable manifolds. You have good contraction for the past in the A minus and in E plus direction. And Z, you just intersect those 2 sets, and those are points where you have good stable and good unstable manifolds, pretty much. And you have this thing called Please lemma, which is actually a lemma from analysis that allows you to prove the following: for any row, if n is large enough, the set, the ergodic components of M, the measure of Z for each ergodic component of M is larger than 1 minus rho. So you actually have large sets, sets of large measure where you will be able to apply these constructions. And this thing is quantified in if you apply the construction for this set of points and you prove the following proposition. For any point in that set, and here is really following the stable manifolds construction by Crevier-Pujals. And then you just try to precise as much as you can of everything that appears in the construction. And you can prove that for any point in that good set, the stable manifold in the center, so you have your stable manifold, which has dimension 2, you intersect with the center, this is going to give you something of dimension 1. So this stable manifold contains a curve with good length. The length is bounded from below by n to the power minus 7. And you also can tell that this curve, it's almost vertical. It's tangent to some cone, to some vertical cone. So this curve is actually something like this. It has good size and good direction. You can also do the same thing for the unstable manifold, and you find a curve inside the unstable intersected with the center with good uniform lower bound. And in this case, it's almost horizontal. So this is the main technical thing up to this point, is to combine all this information you get, trying to use Please lemma, trying to use these constructions, getting better estimates of Lyapunov exponents. You combine all these things to get this statement, which says that for many points, you have good stable and good unstable of uniform size and good directions. So a summary of the local strategy is this. We needed some sharper estimates of the Lyapunov exponents. Then we define a set Z of good points to construct stable and unstable manifolds in the center. Then Please lemma allow us to say that this set Z actually has good measure for any ergodic component. And then we apply the construction of stable manifolds by Crevier-Pujals to obtain precise estimate on the size of these manifolds. But this is not enough to conclude ergodicity. Only with this, you should be able to conclude that there are at most finitely many ergodic components. Now, you want to, so you have those local manifolds of certain size, and you want to go from these local things to something global in a certain sense. And the way to do this is the set of points Z that you obtained before, they actually belong to the good region, to the good hyperbolic region. And you want to say that many points will spend enough time in the good hyperbolic region such that these small curves would grow into something global of large size. The way to capture this is just look at the points that stay for at least from -15 to 15 iterates in this in the good region. So this is captured by this set X here. And the fact that Z has large measure, it had measure like 1 minus rho, implies that the measure of X is positive for any ergodic component. You're doing like the measure of the intersections, then you can obtain that it's positive. So one lemma is that for n greater than 15, so this 15 is just like, forget about it, just some finite number of iterates. For any point in this set, X, if you look at the stable manifold of f minus n of p, well, you don't know what this stable manifold is completely, but what you can tell is that it contains some curve there. So such that the length of this curve is greater than 4 pi. And this curve is almost vertical. And if you do the same thing for the unstable, you can conclude, but now looking at the future, because, so the idea here is that stable are growing if you iterate to the past, unstable are growing if you iterate to the future. So now if you look at the future here, you'll find some curve inside this stable manifold with that are almost horizontal with length greater than 4 pi. And the ingredients here is that Z is contained in the good hyperbolic region, and P in X implies that all these iterates, they are contained in the good hyperbolic region, and you have a good lower size bound for the size of the stable manifold. So what happens is that, so you would have some point here. Let's start with P. So this would be the unstable manifold of some small size at first, n to the -7. And this is the good region. Then you start iterating this point, and that manifold starts to grow. And then it starts to grow. And what happens is that up to 15 iterates, in the worst case, in 15 iterates, your manifold did something like this, actually. And it spins around the torus in the X direction at least twice. If you do the same thing for a stable manifold, but looking for the past, you would get, at the end, something like this, of good size. And they would have some transversality between them in the center, if you just consider them in the center direction. So this is the type of picture you want to get from that statement, and that's how you would prove that thing. So this is ingredient 1, and something that is easy to see is that once your manifold became global in that sense, that it traversed your torus in the X direction, for example, for the unstable, that thing is robust for every forward iterate, because for every forward iterate, there'll be a piece of your manifold that in the next iterate will spin around the torus at least twice. So this thing for the unstable keeps happening for every future iterate, and for the stable keeps happening for every past iterate. A second ingredient is to use that for almost every point in your manifold. If you look at the center manifold, so these are just the torus, the horizontal torus, and you look at the orbit of this torus, this is actually dense in T4, so this should be T4. This is dense in T4. So it tells you that these torus, they are the orbit of a typical torus is dense in T4, because now you have a good picture inside the torus for the future of some points. You have a good picture for inside the torus for the past of some points, and you want to find points where those two torus are close to each other, so that when you add the hyperbolic part of the manifolds, the uniformly hyperbolic part of the manifolds, those pictures actually translate to transverse intersection between stable and unstable manifolds. And this is lemma 1 plus lemma 2 implies ergodicity. And the idea is that up to some iterate, so you pick P1, a typical point of mu1 that belongs to this good set where we can apply these constructions. P2, a good point for mu2 in this good set where we can apply these constructions. So up to some iterates at P1, for example, at some iterate of P1, so Fn of P1, forget P1 here, you would have the unstable manifold doing something like this. Close to it, you have some fiber for P2, F minus N of P2, and the stable manifold will do something like this. And when you add the hyperbolic parts, they will intersect, transverse intersection. Okay. Once you have this, then Pezin's theory will tell you that those measures will actually have to be the same, because this happens for sets of positive measures. So in this last, I don't know, do I have 2 minutes? Whoever is 2, maybe 3.
Okay, yeah, more or less 10 minutes.
Oh, really? Okay, so,
Yeah.
okay. So you work a lot to prove this thing for the example itself. And then you follow the proof and you realize that everything that happened in the proof is actually C2 robust, with some justification, of course, but it's C2 robust. So this actually implies that the system is C2 stably ergodic. You can actually say more. You can say that it's Bernoulli, but ergodicity at this point is enough. And a few comments is that this type of techniques, so if ever in hyperbolic dynamics, is very, very convenient to find transverse intersections between stable and unstable manifolds. You can do a lot of things just with this type of thing. And one thing that you can also do is to say, so this work is about volume preserving diffeels and perturbations in the volume preserving setting. If you go outside volume preserving, these same techniques allows you to prove that this example can have at most one SRB measure in a neighborhood of the system. Another thing is that there is a recent work of Jérôme Buzy, Sylvain Crevizier, and Henri Sarig about measures of maximal entropy. And they have some, I like very much the criteria they state there, because for me, it's very clean that you can look at finding uniqueness of, proving uniqueness of measure of maximal entropy for some systems. You can translate this by finding transverse intersections between stable and unstable manifolds. And so these type of things can be related to proving uniqueness of the measure of maximal entropy. And actually, with this idea in mind, recently I could prove that for the standard map itself, the map has only one measure of maximal entropy. So it's something that, like, you have this Q product, but can you say something about the standard map itself? And the answer is yes. With this type of technique, you can go back to the standard map, but looking at measures of maximal entropy. So I wanted to finish just leaving a few questions. Some of these I think are really, they should be treatable, like something that we can think of. So one is Fn is accessible. This one I'm not sure if it's treatable. I have no idea, and I think it's a hard problem, really hard problem. If you could prove Fn is accessible, then you get stable ergodicity for free using huge technology we have nowadays. So it's not for free, but using some technology we have nowadays. But I don't know if Fn is accessible. If you can find parameters which is accessible, I don't know. Another question is, so you have these philosophies. That theorem of Cross-Vizier-Pujals actually allows you to kind of quantify this type of philosophy that large Lyapunov exponents, in some sense, implies large stable manifolds in unstable manifolds. In a certain way, it quantifies that philosophy. So can we apply that technique to general systems without assuming dynamical coherence? So here I use the fact that I have a center manifold and I look at the dynamics in the center manifold to have a dynamics in a two-dimensional thing, and I construct stable manifolds for this sequence of dynamics of a surface. If you don't have dynamical coherence, then I still think there should be something possible here using fake foliations, but I don't know precise how to do this thing. But I think it's a nice question: is can you apply this technique to more general settings? And a third question, and this one I find very interesting. I really didn't have the time to spend too much time working in this, but I believe there could be something said here that goes back to Puig-Schub's conjecture. Suppose you have accessibility in a partially hyperbolic system with two-dimensional center, and you don't assume center bunching, but you assume large exponents in the sense of like Cross-Vizier-Pujals type of construction. So if you assume large exponents, can you say that it's ergodic? So without center bunching, accessibility, and you're replacing now by you add a hypothesis of large exponents. So this I don't know, but I think something there could be said here, but I don't know what. Okay, so this is what I had to say for today. And then tomorrow we are going to explore this weakly partially hyperbolic world, which is, you can think of this as a system of this type, for example, that has a decomposition of this type. Okay, thank you.
Thank you, David. Very good. Okay. Some questions or comments? Okay, no one. Do you hear me?
Yeah.
So I'll make a comment. That looks hard.
The question?
Your proof with all the estimates looks like it's hard. I mean, if that's the case for 2, 3 is going to be even worse.
Yeah. In certain, again, like, so in my proof, I use a lot of the structure of the system to mix different ergodic components. But maybe maybe there's something to be said if you replace that by accessibility. You replace the global structure of the example I had in mind with accessibility. So maybe something could be said there, because now you have some global structure. But I still think, yeah, I still think there would be many estimates to prove this thing. But I truly believe something could be said here. At least, I think it shouldn't be super hard to get to like finitely many ergodic components, but to have one ergodic components, I still think maybe something could be said. I don't know what.
Are there more questions?
Yes, please. When you showed Viana's examples, one of them wasn't invertible. My question is, how many of those tools doesn't work for the non-invertible case?
So I think Okay, so what I want to say
We
is
don't
that I
have
think
unstable manifolds in
no, yeah, but I think
general.
something could be said if you look at the natural extension of your system and try to construct stable manifolds for the natural extension of your system. So I think something could be said. Oh, sorry. So in the first example for Viana's map, the endomorphism one, actually there are a lot of works based on that type of example, because in that example your center has dimension 1. It's just an interval. So in those cases, this type of things is a matter more of finding good size of passing manifolds in the center, and you don't have to deal with angles. But if you talk about like a 2-dimensional setting where you could have stable manifolds, I think you can apply this type of constructions looking at the natural extension. I think so.
Thank you.
So let's thank Daphne again. Thank you, David. And Jacqueline, please assume your post.
Well, I think we have a break now. Let me check the program. We have a break now, but we will return at 4, a bit before 4, 15 minutes before 4. And we'll have a talk of Marcelo Viana, who's going to speak about 2 issues in partially hyperbolic dynamics. So at 4, we have Viana. Right now we can have a cough break, but each person is responsible for her or his own coffee.
Oh,
Yeah.
Yeah, you are at the bar, so you are in a better position.
I'll order another one, please.
Yes.
See you
So
soon.
David, this work of yours about the measure of maximal entropy, it's you didn't talk much about it, but seems quite nice. It's for the standard map. Did you publish already? No.
Yeah, it's been published last year.
Okay.
And
last year, 2020. I'm completely, this year is already 2021.
Yeah, nothing published already.
Okay.
Yeah, you can prove actually that C2 robustly there exists at most one measure of maximal entropy.
Yeah.
And you can also talk about like a distribution of hyperbolic periodic points and things like this.
Nice, very nice. Yeah. Well, both talks were very good. You did a very good job explaining the big ideas that are hard, but in a very clear way. I think we are enjoying. At least I am enjoying. So I'll take a notice. I'll look on MapSciNet to check.
I'm not sure if you find it on MapSciNet yet. It's being accepted for publication, but I'm not sure if it's.
But I'll look
on Archive you can find it. Yeah, and I think on Archive is the most recent version. Yeah.
Okay. So well, I'm glad that you accepted this task of giving this course.
Oh, thank you for the invitation. I'm happy to be here.
Yeah. Well, we wish you all at UFRJ smelling our particular smell, but having more social talking, and now we could have coffee break and do more questions and discuss a bit.
Yeah.
But well, that's the best that we can do. So everyone, we return at the same link. Pedro, I don't know if you want to ask a question. I don't know, just see that you appear now. But we're asking something? No, sorry. I don't know if you hear, David. I don't hear Pedro.
Yeah, sorry. I had a phone call, so I had to.
Okay.
Yeah, so I didn't. Well, I only had to answer the call when David already had. I don't know why I'm speaking in English. Mas o Davi já estava terminando, respondendo a umas perguntas quando... Agora é um intervalo, não é? Até ao...
Sim. Retornamos às 4 com a palestra do Marcelo.
Ok,
Ok.
está bem.
Então, so, até já.
Até mais.
We come back at 4,
Tá.
a few minutes before 4. Bye bye.
Sim. Até já.